Hello guys, welcome back to my YouTube channel. Today we will solve the remaining numericals of class 12th physics chapter 5 oscillations. So let's see the remaining numericals. A particle performing linear SHM of period 2 pi seconds about the mean position O is observed to have a speed of b root 3 meter per second when at a distance b meters from O. If the particle is moving away from O at that instant, find the time required by the particle to travel a further distance b. So first of all, they have given us the time period of the particle performing SHM, t equal to 2 pi seconds, and they have said that suppose this particle is performing SHM and this is the mean position, these two are its extreme position. So at distance x equal to b, the velocity v is given to us as b root 3 meter per second of the particle performing SHM. So we need to find out the time that is required for the particle to reach at this point. So we know the formula v equal to omega root under a square minus x square. From this we can say that v is given to us as b root 3, which is equal to omega. Now we haven't calculated omega yet, so we know that omega is equal to 2 pi by t, which is equal to 2 pi, and t is given to us as 2 pi. So 2 pi gets cancelled, it becomes 1 radian per second. So we can say that here 1 will come into root under a square minus x square. Now the velocity here b root 3 is given at the point x equal to b. So x square will be b square. Now squaring on both the side, we can say that 3b square is equal to a square minus b square, and taking b square that side, we can say that a square is equal to 4b square, which implies a is equal to 2b. So we got the amplitude of this oscillation. Now in order to calculate the time at point x equal to b, we know the expression for instantaneous displacement x is equal to a sine omega t, which implies x is at point b. So b is equal to a we got as 2b into sine of omega, that is omega is 1 into t. So these things become bb gets cancelled, and if you take 2 this side, it will become 1 by 2 equal to sine of t. So you can take sine this side, or you can directly say that sine 30 is 1 by 2. So sine 30, now 30 degree can be written in radian as 30 into pi by 180, which becomes pi by 6. So instead of writing 30 degree, we can write pi by 6 here equal to sine of t. So sine gets cancelled, and we get t is equal to pi by 6 second. So this is the time required for the particle to come at this point. Now further they have asked us that how much time it will require to go a further distance b. So we need to calculate the time for x equal to 2b, that is for x to go another distance b from here, that is x equal to 2b. So we have been given the time period for this oscillation to be 2 pi seconds, which implies that it takes 2 pi seconds to go all the way from this extreme position to the other side's extreme position and come back, and here is our m. So it will take 1/4 of the time to go from this distance to this distance. As you can clearly see, this is 1/4 of the total distance for which the time period is given to us, correct? So we can say that the time required for the particle to go from mean position to one side of the extreme position is t equal to time period upon 4, which implies 2 pi upon 4, which is equal to pi by 2 seconds. Now in order to calculate the time for which the particle goes another further distance b, we can say that if this is point m and this is the extreme position e, and if particle takes pi by 6 seconds to come here, and we need to calculate the time required for the particle to come another distance b here, and we know the total time for the particle to go from m to e, that is this time pi by 2 seconds. So we can say that t at 2b is equal to the total time t to go from m to e minus the time required for the particle to go from m to x equal to b. that is Tx equal to b. So we can say that, so this will become pi by 2 minus Tx equal to b was pi by 6, which when we calculate comes out to be pi by 3 seconds. So the particle takes pi by 6 seconds to come a distance b from mean position and pi by 3 seconds to come another distance b from the previous position. I hope you understood this sum. Let's look at the next sum. The period of oscillation of a body of mass m1 suspended from a light spring is t. When a body of mass m2 is tied to the first body and the system is made to oscillate, the period is 2t. Compare the masses m1 and m2. So solution, we have been given a body tied with a spring of mass m1, and when this body oscillates the time period is t. So we can say that t is equal to 2 pi upon root under m by k. Now if you wonder how this formula came, we know that omega is equal to 2 pi by t, which implies t is equal to 2 pi by omega. Now we can write it as t is equal to 2 pi under root 1 by omega square, and multiplying m in the numerator and denominator we can say that this will become m upon m omega square. Now we know that m omega square is equal to k, which implies t will be 2 pi root under m by k. So this is how this formula came. Now in the second case they have said that when a body of mass m2 is tied to the first body m2 and the system is made to oscillate, the period is 2t. Now when this two body are oscillating, the time period is 2t, which is equal to 2 pi root under. Now here there was only one mass m1, so we can say that this will be m1 by k. But in the second case there are two masses, so we can say that this time period 2t will be equal to 2 pi root under m1 plus m2 by k, giving it equation 2. Now we need to compare the masses m1 and m2. So dividing equation 1 and 2, we can say that t upon 2t will be equal to 2 pi root under m1 by k upon 2 pi root under m1 plus m2 by k. 2 pi cancel, tt gets cancelled, which implies 1 by 2 is equal to m1 upon m1 plus m2. I hope you understand how we got here. So squaring on both the side, we can say that 1 by 4 is equal to m1 plus m2, which implies m1 plus m2 will be equal to 4m1, and we can say that m2 will be equal to 4m1 minus m1, that is 3m1. Now taking m2 this side and taking 3 this side, we can say that m1 upon m2 ratio will come out to be 1 by 3. So this was a pretty easy sum. Let's look at the next sum. The displacement of an oscillating particle is given by x equal to a sin omega t plus b cos omega t, where a, b and omega are constant. Prove that the particle performs a linear SHM with amplitude a equal to root under a square plus b square. So solution, we know that the instantaneous displacement at any time t is given to us as x equal to a sin omega t plus phi. This is the phase difference, where a is the amplitude. So we have been given x is equal to a sin omega t plus b cos omega t, and from comparing this equation with this equation, we need to prove that the amplitude for this particle performing SHM is equal to root under a square plus b square. So let's try to prove this. So let's give this as equation 1, and let's put a is equal to a cos phi and b is equal to a sin phi. So our x will be x equal to a cos phi into sin omega t plus a sin phi into cos omega t. Now taking a common outside, we can say that this will be sin omega t into cos phi plus cos omega t into sin phi. Correct? Now this is the formula for sin a plus b, where this is a and this is our b. So we can say that this will come out to be sin omega t plus phi, which is our x, which implies that this satisfies our equation 1. So we can say that our substitution of a and b were accurate. So from here we can say that a is A cos phi and B is equal to A sin phi. So let's try to prove this equation now. So taking RHS, which is equal to root under A square plus B square, we can say that this will become A square, that is A square cos square phi plus B square, which is A square sin square phi, and A square is common, so taking A square outside, this will become cos square phi plus sin square phi. Now this thing is equal to sin square theta plus cos square theta, which is equal to 1. So we can say that here only A square is remaining, which is equal to A, and this is equal to our LHS. So we have hence proved this is the amplitude which is given by root under A square plus B square for this particle performing the SHM. Let's see the next sum. Two parallel SHMs represented by x1 equal to solution x1 equal to phi sine 4 pi t plus pi by 3 and x2 equal to 3 sine 4 pi t plus pi by 4. These two SHMs are superposed on a particle. We need to determine the amplitude and epoch of the resultant SHM. So we know that this is analogous to x equal to A sine omega t plus phi, which implies A1 is equal to, let's take this as A1 sine omega t plus phi 1 and A2 sine omega t plus phi 2. So A1 is equal to phi and A2 is equal to 3 and phi 1 is equal to pi by 3 and phi 2 is equal to pi by 4. So the resultant amplitude R is given to us as root under A1 square plus A2 square plus 2A1 A2 into cos phi 1 minus phi 2. So putting all the values, we get A1 square is phi square plus A2 square is 3 square plus 2 into 5 into 3 into cos pi by 3 minus pi by 4. Now solving this, we get 25 plus 9 plus 2 5s are 10 and 10 3s are 30 into cos of pi by 3 minus pi by 4 will give you pi by 12 and cos pi by 12 is 0.966. So 25 plus 9, which is 34 plus 30 into 0.966, which comes out to be 28.98. So 34 plus 28.98 will give you R equal to root under 62.98, which comes out to be 7.93. So they have given us x1 and x2 in centimeters, so the resultant amplitude will also come in centimeters. Now let's calculate the epoch. So the epoch delta is given to us as tan inverse of A1 sin phi 1 plus A2 sin phi 2 divided by A1 cos phi 1 plus A2 cos phi 2. Now putting all the values, we get tan inverse of 5 into sine of pi by 3 plus 3 sine of pi by 4 divided by phi cos pi by 3 plus 3 cos pi by 4, which is equal to tan inverse of phi into sine pi by 3 is sine 60, which is root 3 by 2 plus 3 into sine pi by 4 is sine 45, which is 1 by root 2 divided by cos 5 into cos pi by 3, which is cos 60 half plus 3 into cos 45, which is 1 by root 2, and calculating this, we get tan inverse of 4.33 plus 2.121 divided by 2.5 plus 2.121, which is equal to tan inverse of 6.451 upon 4.621. Now dividing this and calculating the tan inverse, we get tan inverse of 1.396, which is equal to 54 degree 23 minutes. So this is the value of the epoch. Let's look at the next sum. A 20 centimeter wide thin circular disc of mass 200 gram is suspended to a rigid support from a thin metallic string. By holding the rim of the disc, the string is twisted through 60 degrees and released. So we have been given that a mass of 200 grams disc is suspended from a rigid support through a metallic string. Okay, and this is the radius. Width of this disc is 20 centimeter. Radius will obviously be 10 centimeter, and this is curled through an angle of 60 degree and left. So this will twist in the opposite direction when it is released and perform oscillations, angular oscillations. They have said that we need to calculate the maximum restoring torque generated in the string under undamped condition. Okay, and they have also given the value of pi cube, which is we have to take approximately 31. So we know that torque is given to us as tau equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. So let's calculate first of all I and then alpha, and multiplying this both we will get the value of the torque generated in the string. So first of all we have been given a disc of radius r equal to 10 centimeter, which is equal to 0.1 meter, and mass is given to us as 200 gram, which is equal to 0.2 kg, and we know the moment of inertia I for a disc is half mr square, which is equal to half m is 0.2 kg into r square, that is 0.1 square. Now this calculating this we get 0.1 0.1 into 0.1, which will give you 0.001 kg meter square, which can also be written as 10 raised to minus 3 kg meter square. So this is the value of I. Now they have also given us time period for the angular oscillation to be t equal to 1 second, and we need to calculate the alpha also. So in order to calculate alpha, we have a time period t equal to 2 pi root under theta by alpha. Now if you wonder how this formula came for the time period, so when an object performs angular oscillation, its time period is given by this expression, where theta is the angular displacement and alpha is the angular acceleration. So from this we can calculate alpha, that is squaring on both the side will give you t square upon 4 pi square equal to theta by alpha, which implies alpha will be theta into 4 pi square upon t square. Now let's put all the values here. They have said us that the string is twisted to 60 degree, which implies theta is 60 degree, but we want here theta in redan, so multiplying by pi by 180, which will give you pi by 3. So theta is pi by 3, and putting all the values in a similar manner we get pi by 3 into 4 into pi square divided by t square. T is 1 second, so t square will be 1 square. So here we have 4 by 3 into pi square, which will be pi cube, and they have already given the value of pi cube to be taken as 31. So it will be 4 by 3 into 31, which comes out to be 41.33 redan per second square. Now knowing the value of I and alpha, let's finally calculate the value of the torque generated in the string. So tau will be I, which we got as 10 raised to minus 3 into alpha, which is 41.33, which comes out to be 41.33 into 10 raised to minus 3, and writing it we can say that this will be 0.0413 Newton meter. So this is the value of torque that is generated. I hope you understood this sum. Let's look at the next sum. Find the number of oscillations performed per minute by a magnet which is vibrating in a plane of uniform field of 1.6 into 10 raised to minus 5 Weber per meter square. The magnet has moment of inertia 3 into 10 raised to minus 6 kg meter square and magnetic moment 3 ampere into meter square. I think here kg meter square will come, not kg per meter square, because moment of inertia I is mr square. So mass is kg and r square is meter square. So make that correction. So solution, we know that we know when a magnet performs angular SHM, its time period is given by t is equal to 2 pi root under I upon mu b, where I is moment of inertia and mu is the magnetic moment and b is the magnetic field. So here they have given us that a magnet, let's take any magnet, is performing vibration going up and down in the plane of uniform magnetic field. Suppose a uniform magnetic field is passing through here and this magnet is performing vibration, and we have been given the moment of inertia of the magnet, which is equal to 3 into 10 raised to minus 6 kg meter square. Also, the uniform magnetic field B is equal to 1.6 into 10 raised to minus 5 Weber per meter square, and mu, that is the magnetic moment, is 3 ampere meter square. So let's put all the value and calculate the time period. And we also know that in order to calculate the number of oscillation, which is nothing but the frequency, n can be given as 1 by t. So when we calculate this time period, we can easily find out the number of oscillation. So t will be equal to 2 pi root under I, which is 3 into 10 raised to minus 6 upon mu, which is 3 into b, which is 1.6 into 10 raised to minus 5. Now 3 gets cancelled, which will be equal to 2 pi root under. When this 10 raised to minus 6 comes down, it will be 10 raised to 6, and this will become 1.6 into 10 raised to minus 5 plus 10 raised to 6 will be 10 raised to 1, which will be 16. So 2 pi into root under 1 by 16, which when this 1 by 16 comes out of the root, it will be 1 by 4. So t will be 2 pi upon 4, which is pi by 2. So t we got as pi by 2, which implies number of oscillations n, which is equal to 1 by t, will be 1 upon pi by 2, which is equal to 2 by pi. Now putting the value of pi, which is 2 upon 3.142, which will give us 0.636 oscillation per second. Now here they have mentioned in the question that we need to find the number of oscillation performed per minute. So to convert this oscillations per second into minute, we need to just multiply this answer with 60. So n will be 0.636 into 60, which will give us 38.2 oscillations per minute. So pretty easy sum. Let's look at the last sum of this chapter. A wooden block of mass m is kept on a piston that performs vertical vibration of adjustable frequency and amplitude. During vibrations, we don't want the block to leave the contact with the piston. So suppose here in something, here is a piston which can go up and down, and here a wooden block is placed of mass m, and the piston is performing the vibrations, that is, it is going up and down. So we need to calculate how much maximum frequency is possible if the amplitude of vibration is restricted to 25 centimeter. That is, the distance that piston can go from the mean position is 25 centimeter. And in this case, how much is the energy per unit mass of the block? So let's see how we can solve this sum. So when the piston is going up, the wooden block will obviously stick to the piston, but while coming down, wooden block will fall with acceleration g, but the friction will have a restoring force, which is F equal to kx. And in this case, in order to calculate the maximum frequency, they have given that the vibration is restricted to amplitude of 25 centimeter. So we can say that the restoring force of the piston while coming down will be in terms of magnitude kx, as we need to calculate the maximum frequency for which the amplitude is 25 centimeter. Let's take it ka. So this is the restoring force with which the piston will come down, but the wooden block don't have any restoring force. It will just freely fall with the acceleration due to g. In order for the wooden block to stick to the piston while coming down, the force with which the wooden block is coming down due to the acceleration due to gravity should be equal to the restoring force of the piston. If that is the condition, then only they will stick together, which implies that mg should be equal to the restoring force ka. Now we can say that k is m omega square. So we can write this as mg equal to m omega square a. mm cancel. So we get g, which is equal to omega square a, and we know that the maximum acceleration a max has the expression of omega square a, which implies the maximum acceleration a max is equal to only g. That is, we can say that the maximum acceleration with which the piston should come down should be equal to the acceleration due to gravity for the wooden block to stick to it. But we don't want the acceleration, we want the maximum frequency. So from this expression we can calculate omega, and from omega we can calculate the maximum frequency. So G is given to us as omega square A, and in the question they have mentioned that to take G as 10 meter per second square. So instead of calculating omega and then calculating frequency, we can directly say that omega is equal to 2 pi f, which implies omega square will be 4 pi square f square. So putting this value here, G will be equal to 4 pi square f square into A, and acceleration and amplitude is given to us as 25 centimeter, which is equal to 25 into 10 raised to minus 2 meters. So and G they have mentioned here to be taken as pi square. So pi square will be equal to 4 pi square f square into 25 into 10 raised to minus 2. So pi square and pi square gets cancelled, and f square comes out to be 1 divided by 4 into 25. And if you take 10 raised to minus 2 this side, this will be 10 raised to 2, which is nothing but 100. Taking square root on both the side, we can say that f is equal to root under 100 upon 425 is 100. So 100 gets cancelled, and this comes out to be 1 hertz. So this is the maximum frequency, that is f max equal to 1 hertz for the vibration to occur, so that the wooden block won't lose the contact with the piston. Now another thing they want us to calculate is the energy per unit mass of the block. So we know that the total energy for a particle performing SHM is given to us as T equal to half Ka square, where K is the restoring force constant and A is the amplitude. So we know K is m omega square, so we can write this total energy equal to half m omega square A square, and we need to calculate energy per unit mass. So total energy, taking this m this side, will give you total energy per unit mass, which will be equal to half omega square A square. Now from the previous part of this question, we know that omega square A is equal to G, so we can write this as half omega square A into A, which will give us half into G into A, and G is pi square, which to be taken as 10. So half into 10 into A, which is 25 into 10 raised to minus 2. So 2 ones are 2 5s are, and 5 into 25 is 125, and 125 into 10 raised to minus 2 is 1.25. So this comes out to be 1.25 joule per kg. That is, the total energy per unit mass is equal to 1.25 joule for total energy and mass for energy per unit mass. I hope you understood the sums that we did today. Thank you for watching this video, and please like, share and subscribe my channel and comment your feedback. Thank you for your time.